All right, students, today we are going to go over stellar remnants. Our objective for the day is to compare and contrast the final stages and states of stars. So here's what we're going to do first. Remember, last week we went through this here star diagram. Let me go ahead and slide my face up over here so you guys can see it all. We went through the star cycle diagram, okay? What we learned is that everything starts as a molecular cloud and turns into a protostar. After the protostar stage, it's going to either become a low mass star, an intermediate mass star, which is like our sun, or a high mass star. Now, there are four types of remnants, and that's what's going to be found over here at the very right, over here to the very right of our diagram. Not four different ones, technically two different ones. I just misspoke. So what this is we have our white dwarfs, which both our low mass star and our intermediate mass star will become at the end of their life cycles. And then we have our neutron star and our black hole. These are for high mass stars, and they're a little bit different. So we're going to go into detail about them today. We are going to talk about white dwarfs. These typically are the size of Earth, but with a mass more like our sun. 1 teaspoon of matter from a white dwarf would weigh about 5 tons on Earth, so therefore it is going to be extremely dense. It will also be extremely hot, over 25,000 Kelvin, and they will eventually become black dwarfs, and this means that they are going to be cold, and everything that they could have burned would have already been burned out. So this is our guess. Our galaxy is not old enough, based on calculated cooling rates at this point, for black dwarfs to exist. So right now we just know that we have white dwarfs, and we know that at some point this is going to end up burning out and cooling. And then we have our neutron stars. Our neutron stars, they are smaller than the white dwarf, and they are going to be larger than the original star was. They are remnants of the high mass stars. After the supernova explosion, the dense core collapses into a very hot star that is less than 12 miles across. This star will be the size of it across will be less than Colorado Springs, which is where we live. Now, electrons are held by so much gravity they go inside the nucleus. A pea-sized sample of matter would weigh 100 million tons on Earth. So something that is relatively about the size of your pinky nail right here could weigh 100 million tons on Earth, which is an absolute crazy amount of weight here. Neutron stars are going to be very dim due to their size. Since they're very small, it's going to be very, very, very hard for us to see them. And they have a high rate of rotation. Think of ice skating or spinning in a chair. What happens is you bring your arms and legs in. So if you're spinning in your chair, and you spin, and you have your arms and your legs out, that means that you're going to spin a lot slower because you have more you're going further in any one direction at a time, therefore making you spin slower. The tighter you are to the center, the faster you're going to spin. That's why people that are really good at ice skating, when they spin, they're able to get really, really, really tight, so that way then they can spin much, much, much faster. And neutron stars are going to have a very strong magnetic field. Now, neutron stars, radio waves are concentrated at the magnetic poles. Okay, when I say magnetic poles, I'm talking about the North Pole and the South Pole, much like how our Earth has poles. They resemble rapidly rotating beacons emitting these radio waves. Okay, now they're going to do something called pulsate, hence why they're officially called pulsars. Pulsating means that you only see it every once in a while. You see light every once in a while. It's because this thing is spinning around in circles, so therefore the light is not always pointing at you. Aside from radio waves, they can also emit ultraviolet light, X-rays, and gamma rays, all of which are going to be on our electromagnetic spectrum, which will be in the next video. Now let's talk about black holes. These are considered to be the densest objects in our universe. They come from stars that are 25 times the mass of our sun. So these are going to be very, very, very large stars. After a supernova explosion, gravity wins out and collapses beyond a white dwarf. So it collapses on top of itself. And this is going to be significantly hotter than our white dwarfs. Gravity is so strong that light cannot escape gravity. Anything that gets eaten by the black hole emits X-rays before it disappears from our sight. Part of the reason why it disappears from our sight is because it is so dense, almost infinitely dense. Now, black holes, they are gases that are getting pulled into a black hole, form an acceleration disk that spirals around a void while emitting a steady stream of X-rays. These streams are called jets and come shooting out of either side of the black hole. We think the acceleration disks push materials mass back into space. Okay, so this is our acceleration disk out here, and then there's some more things right here. We have relativistic jet, which really kind of just looks like a jet being shot out of this black hole, the event horizon, which is going to be this kind of bulb going over it, and then the singularity, which is going to be this basically void kind of in the middle. Black holes are considered very common throughout the universe. No, we cannot get sucked into one, but they are very, very, very common because we have had stars that have been very, very, very large. And when this happens, they will collapse onto themselves and form these black holes. The earliest stars are thought to have been massive, and their deaths could have provided the seeds that form the supermassive black holes at the center of galaxies. Now, we have a couple of videos here. Okay, here's Death and Remnants video, and then we also have a YouTube video right here. You should watch both of these if you need extra assistance with the work. As you can see, this is kind of a relatively quick part of our unit. We didn't really go over very much because there's really only three types of stellar remnants. We have our white dwarfs, we have our black holes, and we have our neutron stars. All of these are going to be very important, but you should now transition over to your assignment, and please make sure that you do your DLL, so then that way I can mark you as present for the day. That's all I got for you guys today. Have a great day, Stallions.